Today's lesson is translations with vectors, and today is April 27th. The note packet for this lesson has 6 pages, so in case your packet is mixed up, here's our first 3 pages and our last 3. In our last lesson, we talked about a translation, taking our point or figure and sliding it to a new location in the coordinate grid. We used 2 different forms of notation. We used our capital T, and then we used coordinate grid notation, where we said x plus some quantity A, and then y plus some quantity B. We can also describe the translation using a vector. So a vector is going to represent a quantity that has both direction and magnitude, which is known as length. So which direction is it traveling and how far is it going? In the coordinate grid, we can represent a vector using an arrow drawn between 2 points. So in my diagram, if I'm moving from point A to point B, I simply drew a straight line directional arrow telling me where I started and where I ended up. We can also represent or label our vector using a single letter, and it has a little half of an arrow above it. So when we draw in our vector, we want to start at the initial point. So if you look in my grid, I can see that the starting point is A. This would be the tail end of the vector. When we move according to the vector rule, we're not actually going in a straight line path from A to B. We actually have to move according to the coordinate grid block. So in reality, I'm moving 3 blocks to the right. From there, I know that I have to end up at B, so I'm going to move 7 units up to actually get to that location. Once you get to your final location, we call that the terminal point, and that ends the length of the vector. And we can tell that that's the end because that's where the arrow is pointing. If we write the translation in component form, what we're doing is putting together both the horizontal movement and the vertical movement, just like we would in other translation type notation. So there's 2 ways to write it for a vector. The first value is the movement along the x-axis, and the second value is your movement along the y-axis. And signs do matter, just like in regular translation notation. But the vector form, you can see it doesn't use parentheses. It's like a bent parenthesis. The other option is to write it in this format. We don't want to write this as a fraction, but on the top it tells me 3 units right. The bottom says 7 units up. Most people stick with the first version. All right, so we're going to identify the vector components. We're going to name the vector and write its component form. So let's start with A. My initial point is J, and I'm traveling towards K. But in reality, I have to move 1, 2, 3 units to the right, and 1, 2, 3, 4 units up. So the name of this is JK. You have to start with your initial point, and the second letter is your terminal point. And we said 3 and then up 4. So my component form is listed here. In example B, we first want to name it. So again, we're starting at M, traveling to N. So this is vector MN. Now the movement left or right didn't occur, but I still have to represent that somehow. So we'll use a 0. And then I did have to move up 4 blocks. So there's the component form for my translation. In the last example C, we're starting at T, traveling towards S. So the vector's name is vector TS. And then the movement. First, we want to go 3 units right, and then we want to go 3 units down. So 3 right is positive, but 3 down is negative. In this example, we are translating a full figure. We're using the arrow to kind of indicate that vector movement. Just like in the lesson we've just finished up last week, you can pick one point on the figure, whether it's T or S or R or Q, and we're just going to see where it landed. So if I focus on R, we would have to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. 8 to the left, so that's negative, and then 2 up. So we have to write it first in coordinate notation, so that's the older version. The capital T seems easiest, so 8 to the left, 2 up, and then in vector form, same setup. So with a vector, this is a directed line segment. We did talk about directed line segments when we were partitioning, finding point P, 2/3, 3/4, somewhere along the path. So your directed line segment has a length and it can be measured. So even though we didn't move on that straight line path, we could still calculate the straight line distance. So this is the magnitude of the vector, calculating the length. We do write it as the absolute value. So it doesn't matter if I was traveling from A to B in a positive sloping motion, or if I was traveling from B to A. We want to use the absolute value of the distance. And there's the symbol for vector AB. So we know that we're traveling from A to B. In order to calculate the length, in blue, we have two options. One option is to sketch out a right triangle. So I would know I'd have to move 6 units to the right and then 4 units up to actually move from A to B. So with those lengths, I could use Pythagorean theorem to calculate the hypotenuse AB. Or you can simply use the distance formula. We know the ordered pair for A and B, so that might be easier. I chose to use Pythagorean theorem or distance formula instead because that's what I'm used to, but either method would be acceptable. So we're going to find the lengths of the given vectors. We're going to use the Pythagorean theorem. What I've done is I've simplified it a little bit. It would be a squared plus b squared equals c squared. Ultimately, when you get to that final step, we're square rooting. So this version is just a simplified version for you to sub into. So if this is our component form, you could always sketch out a triangle, but this says I'm moving 2 units to the right and then 7 units down. But essentially, the lengths of my legs are 2 and 7. So I'm going to sub those in and square them. So the length of that vector is the square root of 53. We can try another one. So this time, if you want to draw the triangle, it would be -4 to the left and then 11 up. But essentially, my sides are 4 and 11. And squaring, I know that distance is the square root of 187. And of course, if you can simplify the square root radical, we would expect you to do that. In addition to the length of the vector, we also want to know the direction. The direction of your vector is determined by an angle. So it's marked here in the picture with a question mark. You can use theta and how it relates to the horizontal line that it's attached to. So if we're going to find the direction of the vector, we're going to use basic trig. We have our formula, sine, cosine, and tangent. Based on what I see here, though, looking across, 4 is opposite and 6 is adjacent. So you can say that phrase in your head. If we were finding a side length, we would use our regular sine, cosine, and tangent functions on the calculator. When we're looking for an angle, we're using our inverse functions. Make sure you're in degree mode or this will go terribly wrong. So finding the direction of a vector. In our first example, we have the movement of 2 to the right and 7 up. So if we label this, this is 2, and this is 7. We're looking for the angle here made with the horizontal. There's my theta. So tangent of theta, opposite over adjacent. So 7 over 2. Because I'm looking for the angle, I'm using an inverse function. So we're switching theta and our ratio. And when I type this into the calculator, I'm going to round it off. It's about 74 degrees. Based on the structure of this, I have 2 to the right and 7 up. I'm in quadrant number 1, so the angle measure is positive, and that makes sense. If we want to find the direction of this vector, notice the movement x is -5, so I'm actually traveling to the left 5 units, and then I'm moving up 8 units. So again, my theta is here, and we have opposite over adjacent. Oh, and it looks like I set this up wrong. This is 8 over -5. We're going to activate our inverse, so 8 over -5. When I type this into the calculator, we do get a negative angle measure. You might have to hit the equivalent button. This is actually -57, and it's 0.99. So if I rounded it off, this would be -58 degrees. And you can obtain a negative angle measure. That just tells me I'm in quadrant 2, and you'll explore that more in Algebra 2. Now, when we move our figure, you can see in my picture, my triangle had 3 points, 3 vertices. All those points need to move to its new location. So you can see I'm sliding it to its new location in blue. When you use a vector in a translation, we call them free vectors. Basically, every point on that triangle, and it is made up of an infinite number of points, all those points have to move the same direction and the same distance to create an image. What you can see here is that when I draw on the left-hand side my vector to its new location, and do that with the point on top and the point on the right, what I'm creating are parallel line segments. And it's showing the direction of the movement, but all of those vectors are parallel. So when you use vectors in a translation, basically those directional arrows are connecting our pre-image to our image. All the vertices are present on the image, and all of the vectors are parallel. But if you calculated their length, they would all be the same length, and we can clearly see they're traveling in the same direction. So these vectors, because they are the same length and traveling in the same direction, they are considered identical to each other. They don't have to start at the same initial point, and they don't have to have the same terminal point. But because they're moving from the same object to the same image, they're all going to be identical. Your homework for this lesson is homework number 118. It does have 3 pages to it. If you have any questions going through your homework, please feel free to contact me. Please make sure you're submitting homework on a daily basis. Otherwise, have a great day.